Okay, this is the second lecture, or second portion of the lecture for NetworkX. So let me close out that first notebook. So we just finished NX1, so now we're going to do the second one. Click on that. Okay, so we start off with the graph that we had before. I'll go ahead and run that cell. It'll import NetworkX. It'll create that graph for Delaware's counties. And now we're going to add the populations of these counties as attributes to the graph's nodes. And actually, since I created this, the populations have changed. So the 2020 census occurred. So now the populations have changed. So Kent is now that. Newcastle's population is now this one. And Sussex's population is now this. Okay, so we're going to add these populations to the nodes. Okay. So what we'll do is we'll do g.nodes, and we'll want to refer, let's say, first to Kent. And if we want to give an attribute, it'll be just another kind of another index here. So Kent was the first one. Now we'll put in the population, and I'm going to call it total population, or tot pop. That's just kind of a convention I've followed in some other districting codes. So I'll stick with that. So this will be 181,851. I'll do the same sort of thing, but for the other counties. So next up is Newcastle. Population is 570,719. Then Sussex County. Population 237,378. Okay. So that should add those populations to the nodes as kind of an attribute. Now let's go ahead and print them just to check it. So for every node in the set of nodes, we'll print the population of that county, the population of node is, and this will be g.nodes for that other node, and then the attribute that we're wanting to print, which is that total population. Okay. Seems like we're doing good. Okay, so nodes can have attributes. We could add the population. We could add maybe other more specific types of populations, just depending on the demographic group. So I know some teams are working on states that are required by law to draw minority opportunity districts. And so in that case, whatever the particular minority is, you may need to store the population of that particular minority group for, let's say, some of these counties. Okay, but here I'm just writing the total population. Okay, so not only do or can nodes have attributes, but edges can too. So let's see. So I think I went into Google Maps and I calculated what's the distance between two counties. So I think, what was it? Newcastle's the northernmost county. And to go from it to Kent County was about 36 miles. I think this is maybe from the center of the county or the county seat, something like that. Okay, so for whatever reason, suppose I wanted to record that distance between those two counties. So I would need to refer to one endpoint of that edge and then the other endpoint. So this would refer to this particular edge, and then now if I want to give that, in this case, a weight, I would specify the name of that weight attribute here, which I'm going to call distance underscore miles. I'll set it equal to 35.9. I'll do the same thing for the other pair of neighboring counties, Kent and Sussex. That distance in miles is 37. Okay. Now let's print those. So for every edge in a set of edges, I'll print the distance in miles along edge this is that particular edge, and then what we want to print is distance in miles. Okay. So nodes can have attributes, edges can have attributes, and also the graph itself can have attributes. So for this particular graph is representing Delaware, so I could say that I could store that as an attribute. So for this particular graph, this attribute I'm going to call state. We'll record that this is the graph Delaware. And I might also record other properties of the state or the graph. So Delaware, being a relatively small state in population, only gets one congressional district. Okay, so I can store those, and if I wanted to, I could also print them. So the state's name is this. And the number of congressional districts that this state gets is this. Those. All right. Okay, so now we know how to set attributes for nodes, edges, and for the graph itself. And these are sometimes important for other computations that you'll do. The one computation that's important for districting is to know if a district itself is connected. So knowing whether a district is connected is something that you can do with NetworkX. But maybe for now, let's even just check if the entire graph is connected. And it should be, because it's just that path graph on 3 nodes. So let's check that. Is the graph G connected? And then here I'll use this NetworkX function that's called isConnected. And I just have to pass it as argument this graph that I'm working with. And so this function right here is either going to return true or false. So let's see. Should be true, should be connected. And it is. Okay. Then we could ask if districts are connected. So let's suppose that we decided to make a district just consisting of Newcastle and Kent. So I'll put those two, I could put them in a set, or I could put them in a Python list. Either one of these I think would be appropriate. I'll just put it in a list. Okay, so Newcastle and Kent. So maybe let's check. If that were a district, that would be, the Newcastle is on the top and Kent is in the middle. So they do touch each other, so that would be a contiguous district. So if we check that, say, is the district deconnected? And so here we wouldn't pass the whole graph, we would pass the subgraph that corresponds to just the vertices in D. So let's check that. It should be connected, and it says yes. Okay. But what if I did the same thing, but I took not the top county and the middle county, but suppose that I took the top county and the bottom county. So that would be Newcastle and Sussex. So that would not be contiguous on the map, and it would not be connected in the graph. So let's make sure that that's what happens. So that's Newcastle and Sussex. Let's see if that district is connected. It says no. Okay. So NetworkX can tell us whether a graph is connected or whether a subgraph is connected. It can also tell us what are the distances between nodes. So let's say you're at that top node. So that's Newcastle. It takes you one hop to get to Kent County, and it takes one more hop to get to Sussex County. So that we can retrieve using NetworkX. So we'll get the hop-based distance, or I could also, maybe I could also call this hops, but I'll say distance. Okay, so I want to get the distances using this NetworkX function that's called shortest path length. I want the shortest path length in graph G, starting from the source node being Newcastle. And I want to get the distance or the number of hops from that county to each of the other counties. Okay, so I could print that dist. So this is actually a Python dictionary. Let's confirm that. So it tells us if you're starting at Newcastle, to get to Newcastle, it takes 0 hops. You're already there. If you're starting from Newcastle to get to Kent, it takes 1 hops, and to get to Sussex, it takes 2 hops. So I could just print this entire dictionary at once, or I could iterate over the nodes. So for every node in g.nodes, I could say the number of hops from, all originating at Newcastle, to whatever this is the distance to get to that node. Okay. Newcastle to Newcastle is 0, Newcastle to Kent is 1, Newcastle to Sussex is 2. Okay. So we can get hop-based distances in this way. We can also get the like an edge-weighted distance. So we said that it took 35.9 miles to go from the top county to the middle county, and then another 37 miles to go from the middle county to the southern county. So I guess if in total, if you were starting at Newcastle and you're going to Sussex, it would take you 72.9 miles. So let's calculate that using NetworkX. So it'll actually be very similar to what we wrote there. So let's see. So we want the distances in this graph from this source node, but now we need to specify that we're actually using a weight on each of these edges. We're not just counting each edge as a weight of 1. We want to use the weight being what is the distance in miles along that edge? Okay, so now we're not measuring the number of hops, we're measuring the distance. The distance in miles from Newcastle County to that other one is the distance to that node. Okay, so I think the rest of this is correct as is. Let's run that. Okay, Newcastle to Newcastle is 0 miles. Newcastle to Kent is 35.9. Newcastle to Sussex is 72.9. Okay, so this distance function may also be helpful or important for you in the districting project.